look at the beginnings or simple quantum mechanics. Let's start with a single particle in a box, a particle that is localized, sort of like the last problem that we did. But think of like an electron that is localized to an atom, or in general, a particle in a box. So if a particle is localized to a box, we are saying that there is no probability it's outside of the box. And let's just do a one-dimensional box, 1D, just like that last example. So we have a box, and in one dimension, the particle must be somewhere within that box. It can't be outside of the walls. And what that really means is that there's an infinite potential at the walls. So the potential is infinite at the walls, anywhere to the left or right of the walls. Infinite. And maybe the potential is 0 inside at the bottom of the box. That would be the way of localizing a particle to a box, is setting up that kind of potential function. So in order for the particle to be in the box, that just means that its wave function must exist only inside the box. So psi, which is a function of, let's make this x, and we'll just call the one dimension x. So psi, which is a function of x and t, must be localized to within the box, must be in the box only. So we can represent the wave function as a simple sinusoidal function. So psi as a function of x is, let's say that the wave function is just a simple plane wave. This is called a plane wave. So we're just saying we're going to represent it by a simple plane wave. And then what must be true about that wave function? Well, first of all, since the wave function, and we're just going to have to do this at a time, at a we do this, we just say at some fixed time. So we can just choose t equals 0, for example. So at t equals 0, therefore psi as a function of x is equal to a sine kx, in order to figure out what is the wave function of the particle in the box at any time, any instant in time. Now, that's for, but psi as a function of x is, let me rewrite this. It's also equal to 0 if, let's just make this the origin, and let's make the box a width of L. And so if x is less than 0, or x is greater than L, it's equal to 0, and it's non-zero if 0 is less than x, less than L. But what about at the wall? At the wall, this is important. At the wall, since it's 0 to the left of the wall and to the right of the wall, then at the wall it must also be 0. So the function must be 0 at the wall. So what that actually tells us is that if the function is 0 at the wall, you can't have a discontinuous function. In other words, if the wave function, right, which is a simple sine wave, if the simple sine wave was like that, and we say, okay, so it's got some amplitude at the wall, but then over here is, wherever 0 is, it's got whatever 0 is, that would be discontinuous if it went from some max to 0 at the wall. So the wave function must equal 0 at the wall, and what that means is that this must be it must be continuous at the wall. Means that if we put an equal sign, that means that if psi at 0 is 0 and psi at L is 0, that means that a sine k times 0 must equal 0. That's just plugging in a 0 there, and then plugging in L there, a sine k of L equals 0. And what that tells us is that only have half integral wavelengths in the box. So we have, with L, you can only have half a wave or wave. So this is psi equals 0. Or 1.5 waves, etc., because it's always got to be 0 at the walls. So therefore, this condition that the wavelength divided by 2 must be some integer number of those must fit within the length L. So therefore, for the particle in the box, we can say lambda sub n, that there are different allowed wavelengths, but they're all equal to 2L over n. The allowed wavelengths are that. Simply, again, just because that we know that it's confined to the box, so the wave function must be 0 outside of the box. And because it's 0 outside of the box, it must be 0 at the walls. And so if it's 0 at the walls, it must fit an integer number of half wavelengths between the walls. And so then we can go ahead and say, okay, but we also know that the energy of the allowed energies of the particle in a box, which we can call E sub n, which are 1/2 mv squared, and the potential energy is 0, but we could have set some potential energy, but it's 1/2 mv squared. It's the kinetic energy, which is also p squared over 2m, right? That just in case you don't remember, if p equals mv, and therefore p squared is m squared v squared, so therefore p squared over 2m is 1/2 mv squared. And the momenta, the allowed momenta, 1 over 2m, are h over lambda, and lambda, or the momentum of that wave is h over lambda. We've established that previously, but they're only certain allowed momenta, lambda sub n. So therefore, the allowed energies, I'll just rewrite it right here. We have it right above. 1 over 2m, h over, well, I guess I should have, and then we can plug in 2L over n. So therefore, the allowed energies, about to square it, square the momentum, so we get that the allowed energies are this, and then I'm going to go ahead and plug in those so that the allowed energies are n squared h squared over 8m L squared. So those are the allowed energies of the particle in a box, where n, again, is an integer. Okay, so let's do example. Now remember, this is a one-dimensional box, so we haven't done this in 3 dimensions. But let's just say that an electron is confined to a one-dimensional atom of size 0.5 angstroms. That's the Bohr radius. Construct an energy level diagram. Well, so all we mean is to calculate the energies and put them in a diagram. Remember, this is quantized because we've got E sub n equals, and n can only be an integer. So E sub n is equal to n squared times h squared over 8m times L squared, where L is the length of the atom, or the length of confined. So L is 0.5 angstroms, m is the mass of the electron, 0.511 MeV per c squared, and h is whatever h is. And so we can go ahead and plug in and find that the energies are E sub n equals n squared times 152 eV. So therefore, the ground state energy is 152 eV. The first excited state energy is 4 times that, which is 608 eV. And the next excited state, second excited state energy, right? This is called the ground state. This is called the first excited state, second excited state, etc. Or you could just call them first quantum level, second quantum level, third quantum level, etc. So anyway, 9 times 152, which is 1368, and an energy level diagram. I'm just going to do it in the corner. We don't even need to really draw it out, but we've got the first level, the second level, the third level, and the fourth level right there, like that. And the energies are, I guess I didn't calculate the fourth one. We can multiply it by 16. They actually get farther apart as you go up. And the other thing to notice is these are positive energies, not negative energies, because we set our potential equal to 0 at the bottom of the well. If we had set a potential, there was no top of the well, so it was kind of hard to say where to set u equals 0 to otherwise. But if we had a top of the well and we set u equals 0 here, then the the energies would be negative. right? But it's just the fact that where you set u equals 0 is arbitrary. So that's why these are positive instead of negative energies. So I think I'll just stop there. I don't think that we need to do any more. We've gotten to the end of chapter 5. We've started quantum mechanics, quantum 1. We start with particle in a box and the Schrodinger equation, which is chapter 6. And that pretty much does it. Have a wonderful day and week.